In this video, we will be talking about how to find the areas between curves. So to see a visual representation, what we were discussing, if you have two functions and you want to find the area in between them, if you were to take the integral of the top function and subtract that from the integral of the bottom function, then you will find the area that is in between. In the past, if you had a function and you wanted to find the area from, let's say, A to B, what you are doing is you are finding the area of that function to the x-axis. Basically, you're subtracting the integral of this function from 0 because that is the x-axis. So in this case, where the bottom part is not just the x-axis, it actually is a function that is going to be the lower domain or parameter, for example. So in this example, we are wanting to find the area of the region enclosed by these two things. So what we're wanting is we want to know what is the area that is between these two curves. So according to what we just learned, it is going to be the area from the top function, which the top function is going to be 2x minus x squared. And then the bottom function, or this bottom function, is going to be x squared. So what the answer is going to be, or the problem, how you would set it up, is you would take the top function and you're subtracting that from the bottom function. But the easiest way to do it is just to do one integral of the first function minus the second or bottom function. Now the only problem is we're having to figure out what are our parameters. At which places are they crossing each other? Well, we know at this point you can say that that is going to be 0. To find this place, what you're going to have to do is off to the side is you actually will have to set the two functions equal to each other. So I'll get 2x equals a 2x squared by adding x squared. And now, no, I'm not. You want this set to be equal to 0, so I'm going to subtract 2x. So I'll have 2x minus 2x squared set equal to 0. I can factor out a 2 and I can factor out an x. And when I do that, I'll be left with 1 minus x. So when we set them both equal to 0, I'll get x equals 0, which is how I found that number. And then 1 minus x equals 0, which means x equals 1. And so therefore my other parameter is 1. And now I can actually take the integral. So what I'm going to do first is we now know it's from 0 to 1, and I'm just going to combine what I know. Negative x squared minus x squared gives me a negative 2x squared. And now I'm going to take the integral. 2x is going to turn into an x squared because an x turns to x squared, but I have to offset this 2 by making it a 1/2. But there was a 2 in front. And so 2 and 1/2 cancel each other, leaving me just x squared. And now this x squared becomes x cubed. There was a 2 in front, but I have to offset this 3 by dividing by 3. And just to prove that this does work, if I was to take the derivative of x squared is 2x, which is exactly what that is, and the derivative of 2 over 3x cubed, I will bring the 3 down, which cancels the 3, leaving me 2x, and that becomes squared, so that does work. And now I am going from 0 to 1. So I'm going to plug in 1, and then I'm going to plug in 0. So my answer is going to be 1 minus 2/3, which is 1/3. Another example, we are wanting to approximate the area of the region. Again, what we're doing is we are wanting to know the area between these two curves. We know that it starts at 0, but we do not know where the parameter ends. So we know that is going to be from 0 to something, and it is going to be the top function minus the bottom function. So the first thing we do is we need to set them equal to each other in order to figure out what this number up here is going to be. So x over, and we're going to set that equal to x to the 4th minus x. Now, we can solve this, which might take a little bit of time to solve something like this, or we could graph it, and we're looking for the intersection. So therefore, if we were to pull up the graph, we know that it crosses at 0, 0 of both of them clearly, but we need to find what this other point is going to be. So I'm going to find the intersection, and I need to toggle over close to that intersection. So I'm going to get close, I'm going to hit enter, I'm going to hit enter one more time, and hit enter one more time, and the answer is going to be 1.18. So I know that this number right here is going to be a 1.18. And now, that is why they talk about the fact that this is going to be an approximation, is because we're not going to be able to find the exact value. So now what I would do is actually use your calculator in order to plug this whole thing in. From 0 to 1.18, and then it's going to be x divided by minus a parentheses, and then you need to double that parentheses back, and then you're saying that is according to x. Hit enter, and there's your answer at 0.785. Next example, we are finding the area of the region bounded by the curves of sine of x and cosine of x. The green is sine and the blue is cosine, and you're going from 0, which is going to be this point right here, and pi over 2, which is this point right here. So what you're doing is you're actually wanting to find the area of this region plus the area of this region, but you have to be careful. What you're going to have to do is actually have to find where they cross, and then you're going to have to find the two integrals of each. Now, I happen to know where they cross because sine and cosine are the exact same answer, which means they cross each other at pi over 4. I happen to know that this right here must be at pi over 4, that they cross because they equal each other. That's the same point. So therefore, what you're going to do is you're going to go from 0 to pi over 4, and at this point, it is going to be the blue minus the green. And then you're going to find the area of the second part, which is pi over 4 to pi over 2. But in the second area, the green function is now on top, and the blue function is now on bottom. So now you can plug both of those things in, but I'm going to go ahead and show you how to do it by hand. So the interval of cosine is sine, and the integral of sine is negative cosine. And you're going from 0 to pi over 4, which means it is going to be sine at pi over 4 plus cosine at pi over 4 minus sine of 0 plus cosine of 0. So sine is square root of 2 over 2 plus cosine is square root of 2 over 2. So you get 2 square roots of 2 over 2, which is the square root of 2, minus cosine of 0 is 1. Sine of 0 is just 0, but cosine of 0 is 1. So this is the first part. Now we got to do the second integral, which I believe is going to be the exact same, but now we just need to make sure that works. The integral of sine is negative cosine, and the integral of cosine is sine. And now we're going from pi over 4 to pi over 2. So we are going to do negative cosine of pi over 2 minus sine at pi over 2 minus a negative cosine at pi over 4 minus sine at pi over 4. So negative cosine at pi over 2 is just 0 minus 1, because sine at pi over 2 is 1. And then in here, I have a negative cosine at pi over 4 minus sine. So this is a negative square root of 2. So I will get a negative 1 plus the square root of 2. So now what you have to do is you have to combine, because of this plus sign, you're now combining these two. So square root of 2 plus square root of 2 is 2 square roots of 2. And negative 1 and negative 1 give me a minus 2. And that should be my actual answer. Because this is odd, this is even, and they cut in the middle, you could have found just one area, and then you could have doubled it. If you double the square root of 2, you get 2 square roots of 2, and if you double 1, you would get 2. So in this case, it's almost like an even-odd type of function, because each part of the area looks like it mirrors itself. In this next problem, we have a situation. You cannot take the integral unless it's solved for like this is y equals x minus 1. You can take the integral of x minus 1. But to solve for y, in order to take the integral, you have to take the square root. But when you take the square root of both sides, you get a plus or minus, and you cannot take the integral of a plus or minus. So there's a couple of different things you can do here. Here is actually what I'm going to do. I am going to solve for x instead. If I do that, I'll get y plus 1 equals x. And then here, I'll get 1/2 y squared minus 3 equals x. I would subtract 6, but I got to divide by 2. That's how I get that. And so what we're going to do is we're now going to take the integral using these two functions. But most integrals are basically with respect to y. Not with respect to y. Most of these, what we normally do as integrals, is the parameter is going from like this x to this x. But the problem is that this graph actually goes farther to the left than where they intersect. This intersection's fine, but the problem is when you use the x value of this where they cross here, you are leaving out an entire area that's unaccounted for. If you went from this x value to this x value, that means you're only finding out the shaded region of this, and you're missing basically the nose tip. So instead, if you were to do what I just did, all right, so let's go back. So if I take this and I actually turn it 9 degrees, I can now go from this parameter to this parameter, and I can now find the area underneath or in between these two coordinates. because this parameter is a boundary and this parameter is another boundary. Over here on the original, where they crossed, that is not a boundary because we still have an area that is to the left of it. That's where our problem is. But if we were to turn it 9 degrees, we are now looking at this now right here. We are now curious of what our y value is. And then here, we're wanting to know what our y value is. That is going to be the two parameters. So if I set these two graphs or two functions equal to each other, I can figure out where they are intersecting. So I'm going to get everything on one side because I have a y squared. So I'm going to get 1/2 y squared minus y minus 4, which is the same thing as y squared minus 2y minus 8. I multiplied everything by 2, which means that this is going to be y minus 4 and y plus 2 equals 0, which means y equals a 4 and y equals a -2. This right here, over here, was the coordinate, was y is at -2, and this coordinate y value is at 4. So now we know the integral. We are going from -2 to 4, and this is now x equals instead of y equals. And we are taking the straight line is y plus 1. This is the straight line. This is the line that is on top. And then I'm going to be subtracting the 1/2 y squared minus 3. And this is now dy, because we're now solving with respect to y. So you can either put this in the calculator, or I'm going to show you how to do it by hand. So therefore, in this case, well, first I'm going to go ahead and clean it up. I'll have y plus 4 minus 1/2 y squared dy. So therefore, it is going to be the integral of y is going to be y squared, but now I have to offset the 2 by making it 1/2. 4 becomes 4y, and y squared becomes y cubed, and I have to offset the 3 by making it 1/3. So this 1/2 and 1/3 becomes 1/6, and I'm going from -2 to 4. So I'm going to plug it all in. So I'm going to plug in 4 squared plus 4 times 4 minus 1/6 times 4 cubed minus 1/2 -2 squared plus 4 times -2 minus 1/6 times -2 cubed. And then that, put on that in the calculator and you should get, okay, in this next example, we have the velocities known about two cars A and B. What does the area between the curves represent? Okay, in the last chapter, we talked about the fact that if we have the velocity of cars, if we were to take the integral of the velocity, then we will get the distance traveled. So therefore, if we want to know the area between the curves, what it represents, therefore it is going to represent the distance between the cars after 16 seconds. And now we want to know roughly what that answer is going to be. So there's a couple of ways that you can do this, but they specifically said to use the midpoint. So it doesn't tell you how many rectangles to use for the midpoint, so we can guess at what they should be. So we could say that we can take the halfway point of each of these. So this would be 6.5. This one would be, see, 20 plus 13 divided. This would be 16.5. This would be 21.5. This would be 24. This would be 26.5. This would be 28.5. This would be 29. And this would be 29.5. And then the distance between them will be 2 each time, the distance between them. So therefore, we know that is going to be 2 times and you will get 364. In this case, I believe it would be, they don't say if it's feet or mile or whatever it is. It would be a distance of 364. Okay, to recap, find the approximate area bounded by the curves of the cube root of 2x and then 1/8 x squared. Okay, so first thing I'm going to do is graph this just to make sure that we know the boundaries. The cube root of 2x looks like this. And then 1/8 x squared, so this right here is the cube root of 2x. And then 1/8 x squared is going to look like this. And we're wanting to know the area in between these two regions. So we do need to check and see where they cross. And if I was to graph this, okay, we know they cross at 0, 0, and they says that the boundary is from 0 to 6, but I think they don't cross at 6. So if I toggle over close enough, they actually intersect at 4. So here's the problem. This is from 0 to 4. But they want to know the boundary. They want the boundary to be to 6. That means at 6, that means we have 2 areas that we're dealing with. So what it's going to be is from 0 to 4, it is going to be the cube root of 2x minus 1/8 x squared dx. Plus the area from 4 to 6 is now going to be the red function minus the other function. So you're going to find the area from 0 to 4, and then you need to find the area from 4 to 6 in your calculator. This one you'll get about 3.33 repeating, close to it. And this one you'll get 2.03. So if you add them together, you will get roughly a 5.36 area.